Hey there, Chem 112. We're going to go through practice exam 1A. Let's get into it. So I'm just going to go through the problems one by one. And our first problem is asking, what statement is true for a reaction that has a change in energy less than 0? And so that's the same as saying a negative delta E. And so as you can see here, I started to draw a reaction coordinate diagram. And so if we start with our reactants at some energy level, for a negative delta E, we are looking for when the products then are at a lower energy level than our reactants. And so we'll end up with a reaction coordinate diagram that looks something like this, where here we have our reactants on the left, our products on the right, and we can see that we have one transition state here at the peak. So here it says the reaction will always proceed rapidly in the forward direction. And so to think about this, what I would consider is the case where maybe we are exergonic, energy is exiting our system, but what if our activation energy barrier looked something like this instead? We would still have the same delta E, but now we'd have a way bigger activation energy barrier to overcome, so the reaction would go really, really slowly. Okay, so this is not true. You can have really slow exergonic reactions. And then the second statement says the products have a lower energy than the reactants, and that's going to be true. And also we can have a different way to look at that by thinking that delta E is going to be equal to the energy level of the products minus the energy level of the reactants. And so for this to be negative, our energy level of the products needs to be lower. And then this third statement says the activation energy is smaller for the reverse reaction than for the forward reaction. And so we can see for the forward reaction, we have to put in about this much energy. But for the reverse reaction, we would have to start down here now and put in all of this energy. So this is for the reverse, and we can see that the reverse reaction has a much greater barrier to overcome. So this would be false, making the answer to this question just A. So now let's look at the next question, which asks which graph would be linear if we're looking at a second order reaction. And the only way we know that it's second order is just because they told us in the problem. Then here I wrote the second order integrated rate law. And so this is how we would kind of keep track of how the concentration of a second order reactant changes over time. And it is a little strange to have the 1/overs maybe, but what's nice is that we can write this as y equals, this will be our b plus mx. So it ends up being a line. So if I were to take this equation and draw a graph with it, I'm going to need to have 1 over concentration on the y-axis, time on the x, and then because we have that plus KT term, this will be positive. And then my y-intercept will just be 1 over the initial concentration. And so that means that plot D then would be our linear graph. In this third problem, we have a reaction coordinate diagram again, and we're trying to figure out how many intermediates are shown in this profile. So let's just go ahead and label everything. So we know we're going to start here with the reactants, and then we'll end with the products. And then our peaks here are going to be transition states. And that's when the molecules are twisted and contorted in really strange kind of formations along the way to making or completing the step. And then in these valleys, we have the intermediates. And so the intermediates are real molecules that we make along the way. We make them and then use them up in a later step. So we'll see here that we have 2 intermediates. Those are just the valleys in between our 3 steps. Okay, so here we have a mechanism, which just means we took a kind of complicated overall reaction and broke it down into the individual steps that it takes along the way. And we're trying to figure out what the overall reaction is. And so what we're going to do is just look for any intermediates that might cancel out. So here we can see that we have NO3 being made, and then it is subsequently used up, making it an intermediate and something that we can cancel. And in the second step, we make some oxygen, but then we use some oxygen later on. So we can sort of cancel them. What we'll do is we'll cancel this one and change this coefficient to a 1. We'll just get rid of it. And so now that we've kind of thought about how we're going to cancel, we can go ahead and combine. So we'll have our N2O5, and then we'll have just 1 oxygen. And they will react then to make now 2 NO2s, because we make 1 in the first step and then 1 in the second step. And then we also end up with O2 gas. So this will be our overall reaction as this mechanism is written, and that would correspond to answer choice D then. Okay, so number 5 is asking why changing temperature increases the reaction rate. So let's just look at each statement. The first one says the overall energy change is greater at higher temperature. That doesn't really make sense anyway, because the overall energy change is not going to affect the rate of our reaction. What affects the rate of our reaction in terms of energy is the activation energy. Okay, so this one is out. B says the activation energy is greater at the higher temperature. And we're going to see that that's not the case. And I think we'll talk about why in a second. So B ends up being false. C says more molecules have sufficient energy to form the transition state at the higher temperature. And this is going to be the correct correct answer. So what happens is if we have our reaction coordinate diagram and there's this activation energy, and that barrier we need to overcome, if our molecules are moving around faster, there's a higher probability that they'll collide with enough energy to then get up over the hill. Okay. And then answer choice D says the reaction becomes exothermic at higher temperature. The temperature is not going to change whether it's exothermic or not. E says heat catalyzes the reaction at the higher temperature. This is a bit of kind of muddling some different chemistry terms together. To really be a catalyst, what you would have to do is change the pathway for the reaction. So that rather than looking like the diagram on the left, maybe you look more like this. It's a pretty bad drawing, but the idea is that multiple steps with lower activation energies. And so E is not going to be the answer. Okay. 6 here says, what is the activation energy for the following reaction in the reverse direction? So when we're looking at the reverse direction, we want to start from the products. We're going to start here. And then the activation energy is going to be how much energy it takes to go from our starting point, which are the products in this case, to the peak. Okay, so we're going to have to put in these 92 kilojoules and then also put in those 105 kilojoules. So our activation energy for the reverse will be the sum of those two values. Which ends up being 197 kilojoules per mole. Okay, now we're at number 7, and we have this reaction, and they're asking us something about NO. Okay, and then if we look at our answers, though, we see that they're written in terms of all different molecules, not about NO. And so when we're thinking about kind of switching between the perspectives of different molecules, we'll have to use the stoichiometry. And so if we were to write it out where we have everything equal to each other, we could start with our first reactant and say it's going to be negative for the rate because it's going away. And what we're going to do is we're going to say 1 over the coefficient, so 1 over 4 times the change in the concentration of ammonia over time. Will be equal to now the part for our next reactant, which will also be going away. We'll have 1 over its coefficient times its change in concentration over time. And then now we can write for our products. So these are going to be positive. We'll do 1 over the coefficient times the change in its concentration over time, equal for our next product, positive again because it's appearing, 1 over its coefficient times its change in concentration over time. So now we have this long kind of equivalence relating all of the different things together. And what we are interested in, of course, is the term for NO. And so what we're really trying to find here is just the delta NO over delta T. Okay, but let's look. We have it being related instead to all these different things. So let's just go ahead and start with ammonia. So if we kind of ignore the other things, we can say that negative 1/4 times our change for ammonia over time is going to be equal to 1/4 times our change in NO over time. Okay. And so we can see the 1/4 would cancel. And so we would just see that negative delta NH3 over delta T would be equal to our delta NO over delta T. Okay, so we get that from just simplifying. Okay, and we do see that this corresponds to answer choice C, but let's look if we were to do it in terms of water or oxygen instead. So if we were to write this out for oxygen, we would have negative 1/5 delta O2 over delta T be equal to 1/4 delta NO over delta T. So if we were just interested in the delta NO over delta T, what we'd have to do is multiply both sides by 4. And so we would end up with negative 4/5 delta O2 delta T being equal to our delta NO delta T. And so then finally, if we were to do this for water, we can see from our expression up above that we'll have 1/4 delta NO over delta T equal to 1/6 delta H2O over delta T. Oh, yes, okay, cool. So then if we were to solve just for delta NO over delta T, we'd have to multiply our 4 on both sides again. And so we would see that we'd have 4/6 delta H2O over delta T equal to delta NO over T. Okay, and that would be the same then as 2/3. And I mean, we already found the answer, but we can see that none of these match up with what we just solved. So we again see that C is the correct answer here. Sorry, that's a lot of pink writing in a little space. Okay, next up, we have number 8, where we have this reaction and they give us some starting amounts, they give us some progress, and they want to figure out how much of the S2O8 minus remains at 400 seconds. And so we're going to have to do something kind of similar to the last problem, because the data that they've given us are instead for iodide. We're going to have to relate the iodide change to the S2O8 minus change. And so what we can do is, say S2O8 is going away. We can do 1 over its coefficient, which is just 1. We'll have our change S2O8 minus over time is going to be equal to 1 over the coefficient for iodide. It's also going away because it's also a reactant times its change over time. Okay. And so what we're really trying to find is kind of this numerator up here, the concentration of S2O8 minus, and how much it's changed. So that then we can kind of use how it started, how it changed to figure out how it ends at 400 seconds. And so what we can do is figure out how much the iodide has changed. So our change in iodide is going to be our 0.057 molar iodide minus our 0.072 molar iodide. And we can see that that ends up being negative 0.015 molar. So we know how the iodide changed. We know our time because that was just between our 0 point and our 400-second point. And so we can go ahead and figure out how much the S2O82 minus would have changed. So this is what I'm going to solve for. My time is 400 seconds. Negative 1/3. My change, which is what I just solved for above. Also divided by those 400 seconds. And so what I'm going to see then is that my change in S2O82 minus is going to be equal to 0.005 molar negative. It's going to be going away. This is the reactants. We do expect the concentration to go down. So then I can go ahead and use my initial concentration, which was then 0.05 molar, and combine it with my change. And see that my final concentration then will be 0.045 molar. So we had to use the stoichiometry to figure out how the rates of change would compare, and also then use our initial concentration. Someone asked if you would post the lecture. Will you post the lecture from today? Okay. Someone emailed me about it. Okay, so let's go ahead and look at number 9. We have a mechanism again. And here we have our overall equation given. And so they want us to figure out what the role of each of these three compounds is. And we can see that none of them appear in our overall reaction. And so that means none of these can be reactants or products. And so what we have to do now is figure out whether they're intermediates or catalysts. And so an intermediate is something that's going to be made and then used up again. And so if we look, say, at this NO2, here we can see it's made in the first step, but then it's used up in the second step. So NO2 is going to be an intermediate. So we can rule out option choice C. And then if we continue to look, we can see that in step 1, our NO enters the reaction, but then it's regenerated later. So since it's being used and then made up again, that is going to be a catalyst. So this is going to be an intermediate. It's going to be a catalyst. So now we have to look for just the oxygen, and we can see in the second step it is made and then it's used up again. And so that is going to be an intermediate. So it can be a little tricky to look for these things, but just keep in mind that intermediates are made and then used. Catalysts are used and then made. And that's so that catalysts can go on and find another reaction and keep speeding them up. Okay, so the answer choice here is B. In question 10, we have the dimerization reaction to form N2O4. There's a great homework question about this reaction. But here they give us the rate law, and they're asking us what will change K. So we can see that this is a second order reaction. They're not asking us about order, they're asking us about K. And maybe you remember that there is an equation for predicting K, the Arrhenius equation, which is A times E, so negative EA over RT. And so we haven't talked too much about A, but what it is it's called the Arrhenius factor, but it's a statistic term. So it's specific for each reaction, and it kind of predicts how likely a particular collision is to have enough energy in the right orientation and stuff. And so changing A would change K, but we're not really going to look at that in Chem 112. If you go on and take a biochemistry class, you'll definitely look at it. And then here now we have activation energy, R and T. So let's look at this. Would doubling the pressure of the reaction chamber affect K? I don't think so, nope. If anything, it would change the partial pressure of the NO2, maybe. Okay, B says adding more NO2 to the reaction chamber. So again, changing the reaction, or the amount of NO2 in the reaction will change the rate, but not the rate constant. So that's out. Adding more N2O4 to the reaction chamber. So, you know, N2O4 doesn't appear in the rate law because it's a product, but then also, you know, K doesn't have anything to do with the concentration, so that's out. Reducing the volume of the chamber would be like A, be similar to increasing the pressure. Okay, so it'll change the partial pressures and such, but that's not going to affect K. Then in answer choice E, we can see that increasing the temperature would increase K. It gets a little bit muddled in this equation because you end up with a negative 1 over in an exponent. But we do know that increasing temperature will increase K. And we know that increasing temperature speeds reactions up. because now it's a higher probability that those reactants bump into each other with enough kinetic energy to get over the activation barrier. Okay, so E is indeed the correct answer. Okay, and so now we have the question that you've all probably been waiting for, which is the table of data question. And so we're trying to figure out the order for each of these three reactants. And so what I've done here is just written, rate is going to be K times A to whatever its exponent ends up being, times B to the power of whatever its exponent ends up being, times C to the power of its exponent. So what we want to do is focus on just one reactant. So let's start with A. And we want to pick, two experiments to compare where only the concentration of A changes. And so if we look between 1 and 2, we can see that the concentration of A is doubling, while the concentration of B doesn't change and the concentration of C doesn't change. That way we can isolate the impact that A has on its own. And so we can see that as we double A, we quadruple the rate. So the rate is changing with the square of A. It's going to be second order. And usually for Chem 112 purposes, if how you change the concentration doesn't match how the rate changes, it's probably second order. Okay, so now we want to forget about A and focus on B and pick two reactions to compare where only B changes. And that's going to be between reaction 1 and 3. So we can see A stays the same, B triples, and C stays the same. And so then if we compare how the rate changes, it stays the same. So it changes by a factor of 1. And that tells me that B has 0 impact on the rate, and so it is 0th order. So now finally we have to compare for C, and for that we're going to compare experiment 2 and 4. That's where C changes, but B doesn't, and A doesn't. So we can double C. And then we can compare the rate, and we can see that the rate also doubles. And so C must be first order. So our rate law is going to be K times A squared times C to the power of 1. So we can just eliminate B because it's not doing anything. And that gives us D as the correct answer. So now we have the follow-up to that question, which is to figure out what the K is. And so let me go ahead and write our simplified rate law, which is just K A squared times C. To determine K, we're just going to pull the data from one experiment, plug our numbers in, and then solve for K. So I'm going to go ahead and pick experiment 4. Doesn't matter what experiment you pick. I just usually pick the one on the bottom because it's easier to look at the numbers there. Doesn't matter. But so my rate in experiment 4 was 9.6 times 10 to the minus 3 molar per second. K is what I'm trying to find. I need my concentration of A, which was 0.06 squared, times my concentration of C, And so now all I have to do is solve for K. And so when we solve for K, we'll find that its value is 22.2, and the units for a third order reaction, one it being molar to the -2, seconds to the -1, corresponding to answer choice A. Okay, here we have some reaction and they give us the rate law. It happens to match the stoichiometry of the reaction, but won't necessarily. And they're asking us how the rate will change if we double A and triple B. So what I've done here is I've taken the rate law and I've just plugged in how they would change. So like 2 times and 3 times. And so if we were to, expand this, we'd have, this would be 4 times and then 3 times. And so this is going to end up being 12 times faster. So the answer here is just E. Okay, so pretty simple. You just have to make sure you remember the order. And so here, number 14, we have a 2-step mechanism, and they've told us the first one is the slow step. And so this is going to be the rate determining step. And so let's go ahead and just figure out what our rate law is. I kind of started that below, but it's actually really convenient when the first step is the slow step because you can just go ahead and use the stoichiometry to write it. So here we have ICL to the power of 1 times ICL to the power of 1. So I'm going to say ICL2, which would be ICL squared. And so only changing the concentration of ICL should change the rate. So let's look at these different statements. The first one says the reaction rate stays the same when H2O is doubled, H2 is doubled and ICL is held constant. And that would be true because if ICL is held constant, it doesn't matter what H2 is doing, it's not in our rate law. Okay. So this statement is true. Second statement says the reaction rate quadruples when ICL is doubled and H2 is held constant. So, if we were to double the concentration of ICL, we would have a 2 times the concentration there squared. So it would end up being 4 times faster. Similar to what we saw in the last problem. And so this statement would also be true. And then in the third statement, it says the reaction rate doubles when ICL is doubled and H2 is held constant. And so we saw just a second ago that the rate would go up by 4 times when we double ICL because it's second order. And so this would be false. And C would be our correct answer. This would have been a little more complicated if our second step were the slow step, because then we would have to do our full mechanism evaluation where we are sure to get rid of intermediates and such. So the fact that it was the first step for the slow step made it a little bit simpler. Okay, we have another mechanism. And hey, we can see what I was talking about on that last one, because now our second step is our slow step. And we have to use these steps to figure out what our rate law is. We can't necessarily use the stoichiometry of the reaction given above. And so since the second step is our rate determining step, I'm going to start by just writing the rate with that. So I'll say rate is going to be equal to K times NOBR2 times NO, both to the power of 1. But I can't leave my rate law like this because here I have an intermediate. And I don't want to include intermediate in my rate law. I want to include reactants because those are the things that we're actually scooping into our beaker. And so what I'm going to do is look here at this fast reaction. So this fast reaction is stuck behind the slow step. And it's bored, or that's how I think of it. It's bored, and so it's just pacing back and forth, just going back and forth, back and forth, back and forth, waiting for its turn to go. And so that's when we say it's at equilibrium. And so equilibrium just says that our change in the forward direction is equal to our change in the reverse direction, or a rate of change. And so I can say that the forward rate law, which would be K NO Br2 for that reaction, is equal to the reverse rate law. And now I have a connection to that intermediate that I need to get rid of. So really I'm going to solve for NOBr2 by just dividing this K over here. Though we really don't need to keep track of the K's very much in Chem 112. Then now we can take this whole term and plug it in for NOBr2. And so what we'll end up with is some K. Sometimes we call that K observed. Don't stress about it, it's a K. And then we'll have NO Br2 times NO, which can be simplified as K times NO squared times Br2, which would be C. And so don't get too hung up on the K's, but I do want to say real quickly that Chem 112 ends up being a class all about the letter K. So lots of K's to look forward to. Okay, so here in 16, we have another kind of mechanism question where they've given us a reaction coordinate diagram and we're supposed to figure out which mechanism could match. So looking at this reaction coordinate diagram, I can see that there's two steps. I have step 1 and step 2. And from this diagram, I can figure out which is the slow step. So if I look at the activation energy for the first step, it's smaller than the activation energy for the second step. And so that tells me that step 2 is my slow step. So just from that, we can eliminate some of the answer choices. And so now we need to figure out which would match the information given above. So something they do tell us here is that we have a catalyst in our reaction, catalyst G. And so for G to be a catalyst, it needs to be used and then remade. And so if we compare C and D, we can see that C has catalyst G come in and then it spits it back out, which is consistent with having it be a catalyst. Whereas in D, it uses it, but it doesn't spit it back out. Okay, so that would be acting more like a reactant than a catalyst. So D isn't the right answer and C is. Here in number 17, we have reaction between A and B. So they don't have it written out, but they just say we have some reaction between A and B to make products. And they give us these graphs and we have to write the rate law. And so what we are going to use these graphs for is to figure out the order of our reactants. So here we can see that we're looking at A. And the graph that they've given us is the version where we have the natural log of concentration versus time, which would correspond to this first order integrated rate law. So A must be first order. And then if we look now at B instead, we can see we have a 1 over concentration and time graph, which would correspond to the second order rate law. And so B must be second order. So then if we combine that info to write our official rate law for this reaction, we end up with K times A to the power of 1 times B squared, which is answer choice B. Here in number 18, we're looking at acetaminophen. And they tell us that this conversion process has first order kinetics. And so I've gone ahead here and written our first order integrated rate law. And they give us the half-life. And then they're saying we have, 300 milligrams of our reactant. And we're trying to figure out how much of it would remain after 5 hours. Okay, so if I were to kind of organize my variables, you can see that my T1/2 was 1.7 hours. My time is 5 hours. My initial concentration is 300 milligrams. And then I don't know what my concentration to later time is. That's what we're going to try to solve for. And so you'll notice that I also wrote this other version of the first order integrated rate law equation. And this version just helps us avoid having to find K. Both are fine. They're equal. It's just nice sometimes to skip the conversion. And this just comes from doing some substitution with the first order half-life equation. So if you prefer to solve for K and use the original integrated rate law, that's totally fine. That's great. Both work. Okay. And so when we set this up, what we're going to have is natural log of what we're trying to solve for divided by our original amount, which is going to be 300 milligrams, equal to negative 0.693 times 5 hours divided by our half-life, which is 1.7 hours. And so when we solve this, we'll see that the natural log of AT over 300 is equal to negative 2.04. We want to undo the natural log, so we'll need our exponential. We'll do e to the power of both sides. We'll see that AT divided by 300 is equal to 0.13. And then we'll just multiply by 300 to get our final answer. And we'll see then that AT ends up being about 39 milligrams. Which corresponds to answer choice D. Like I said, if you prefer to solve for K and use the original first order integrated rate law equation, that's totally fine too. So here we're looking at an experiment that Kyra runs, and it's an 80 ml container with some amount of A and B, and after 10 minutes there's this much B present, so what's the rate of disappearance of A? So they're giving us information about B, then asking us about A. So we're gonna have to use our stoichiometry eventually to compare these two. So what we can do is say A is a reactant, so it's going away. Do 1 over its coefficient times its change in concentration over time will be equal to negative, because B is also a reactant, 1 over its coefficient times its change in concentration over time. And then what we eventually want to find is just this part, delta A over delta T. Okay. So it looks like for B, we start with 0.08 moles. And as the experiment runs for 10 minutes, we end up with 0.06 moles B. So we know our change in time, and we're close to knowing our change in concentration, but we have to be really careful because here we have an 80 milliliter container. And so we might have lost 0.02 moles of B, but that happened in an 80 milliliter container, which is the same as 0.08 liters. And so our actual change in B that we want to use is going to be 0.02 divided by 0.08, which is 0.25 molar. So you do have to be really careful with the units here because we definitely need molarity, and we can see that in the units and the answer choices also. Okay. And so then if we want to get delta B over delta T, we'll just divide this by our 10 minutes. But oh no, we don't want minutes, do we? We need seconds. So we have seconds in our answer choice. So we'll have to use our knowledge of the clock and say that for every 1 minute there will be 60 seconds. Okay, and so then we can cancel our units of minutes and get our official delta B, delta T. And this should be negative because it's going away. And this ends up being 4.17 times 10 to the negative fourth molar per second. Okay. But we're not done. All we've done is figure out the rate of change for B. We need the rate of change for A. So this is when we're going to use this equation up here. So we can go ahead, kind of simplify, rearrange, whatever you want to call it, to say that delta A over delta T, which is what we're trying to find, is equal to 3/2. So I multiplied that 3 over delta B, delta T. So what we're going to have then is just 3/2 times this number I calculated. Okay, 4.17. And we end up with a change for A equal to 6.25 times 10 to the negative fourth molar per second. And if you lost a negative along the way or something, it doesn't matter because we're always going to report rates as being positive numbers. Okay, so we have to use the stoichiometry, but then we also had to be really careful with units in this problem. So we had to take our moles, make it molarity, we had to take our minutes and make them seconds. Okay, here we have a graph. I love graphs. And if we look at our axes, which is always the first thing you want to do with any graph, we can see we have the natural log of k on the y-axis and 1 over t on the x-axis. And so this isn't a first order integrated rate law plot. Just because the natural log's there doesn't mean it's first order integrated rate law. This is instead the Arrhenius equation, which I've written here. And we can think of this then as y equals mx plus b. And so here they're asking us about the activation energy. And so we're going to need to use the slope. And so then what we'll say is this whole part here is the slope. And so that negative 1.61 times 10 to the fourth is going to be equal to negative EA over R. So the R that we use most often in Chem 112 is the 8.314 joules per mole Kelvin. I'm going to plug that in here. And so then to solve for activation energy, the negative signs cancel. I just have to multiply over the 8.314. Which gives me a value of 1.34 times 10 to the 5th. And maybe you're unsure of what the units are. So this is really in units of Kelvin. The kelvins end up canceling and we end up with joules per mole. So then we can see the answer choices are actually in kilojoules per mole, but that's fine. We can handle that by just adjusting for a factor of 1,000. And we can see that the answer is B. Okay, so don't forget, you can't just directly use the slope here. You have to adjust for R. Okay, here we have a second order reaction, and we just know that because they told us. They give us the half-life and the initial concentration. Ooh, silly pen. Okay. Go ahead and erase that. Okay. Oh, come on, Mr. Pen. Okay, sorry, glitch. No, stop glitching. Oh, man. Okay. When in doubt, turn it off. And then turn it back on again. I have to admit, though, of all the ways this pen has glitched over the years in Zoom University, that is probably the most fun one. Okay, looks like we're back. Sorry. So, back to our second order reaction. They want us to figure out the rate constant, and what they've given us is half-life and initial concentration. And so for the second order half-life equation, we have 1 over K times initial concentration. And so we know that, we know 3 or 2 of these things, and we're just trying to find the third. So what we can do is say, we have 18 seconds equal to 1 over K, which is what we're trying to find, times our initial concentration of 0.71 molar. So we can multiply over by, or multiply our 0.71 over, and we get 12.78 equal, and this will be seconds times molarity, is equal to 1 over K. And so then to undo the 1 over, we're just going to do 1 over on both sides. And when we do 1 over 12.78, we get that K is equal to 7.82 times 10 to the negative 2. And then now we have to do 1 over molarity and 1 over seconds, which would correspond to answer choice A. Okay. Okay, so here in problem 22, we now instead have a first order reaction. And so I've gone ahead here and written the first order integrated rate law. And we're given the information about how long it takes, 42 minutes, to change from 0.45 molar to 0.32 molar, which is all well and good. But then they're asking us about how long it will take for the reaction to be 90% complete. So now they're asking us about a different scenario. So what we're going to do is use the first scenario to solve for K, and then we can repurpose that K to answer the question. So I've already organized some of the information. So here I have my initial concentration, final concentration, and time. So I'm going to plug those into this first order integrated rate law to solve for K. So I'm going to have the natural log of 0.32 molar equal to the natural log of 0.45 molar minus K times 42 minutes. So then I can go ahead and use that equation to solve for K. And I find that it is 8.12 times 10 to the negative 3. That is going to be minutes to the minus 1. And so now that I have the K, I'm going to have to think about my next set of conditions. So I know what K is because I just found it. Time is what I'm trying to find. And now I'm going to have to be careful about what to use for my concentrations because they didn't really give me concentrations. They just said 90% of the reaction is complete. And here's where you have to be really careful. Whenever they give you a percentage like this, you have to be super careful. Because when I read this, what I actually see is how long will it take for 90% of the reactants to be used up? Or in other words, how long will it take for 10% of the reactants to be left over? Because what we want to do is our initial concentration and then our concentration that's left after the time in our integrated rate. So if we were to start with, say, 1 molar, what we'd have left actually is just going to be 0.1 molar of our reactants. So you do have to be a little careful there. And then we can plug that information into our integrated rate law. And it's nice in a first order reaction, you can go ahead and pick whatever initial concentration you want, which is, I picked 1 molar just for simplicity. If it were second order, we would have to use the actual values given. Okay. And so then once we have this set up, we can just go ahead and solve for T. And we get that T is equal to 283.6 minutes, which is answer choice E. So here we have a question where we're looking at the activation energy of some reaction, and we're thinking about changing the temperature and seeing how much the rate would change. And so for that, we're going to need the Arrhenius equation in the version where you combine 2 of them. And so here I have that. It looks a little different here than on the data sheet. And that's just because I wrote that my temperature and my K, or my K on top, is going to be the one at the hot temperature because that's the one that's going to go faster. And it's nice to be able to say something goes 5 times faster than to say it goes 0.2 times slower, just sort of a double negative. So I like to put my K that I know is going to be faster on top, which is always going to be the hot one. And so here I have this equation, and it looks like there's a lot of pieces, so it's always nice to just organize the information to begin. So I have my activation energy. I have then the R value from the data sheet. And I know R has joules in it usually. And so I want it to match the activation energy units. And if I just left it in joules, they wouldn't match. So I'm going to change it to be in kilojoules. If you prefer to change activation energy, that is a-okay. As long as they match, doesn't matter if it's joules or kilojoules. And then I have my cold temperature, which is 4 degrees Celsius. But of course I want that in Kelvin instead of Celsius. And the same goes for my hot temperature. Okay. And so now it's just going to take a minute to, punch everything into that equation. And so here I'm going to have, the natural log of K hot over K cold. So I need my activation energy, which is 106.9 kilojoules per mole divided by R. Times 1 over our cold temperature, which will be 1 over 277 Kelvin, minus 1 over our hot temperature, which is 298 Kelvin. And so, being really careful with order of operations, I'm going to go ahead and just solve for what the right side is equal to. And that ends up being right here. .27. And so to get rid of this natural log, now I'm going to need my exponential again. So I'm just going to say that then K hot over K cold is equal to e to the power of 3.27, which ends up being 26.3. So we would say at the higher temperature of 25 degrees Celsius, the reaction proceeds 26.3 times faster than it does at 4 degrees Celsius. And the correct answer, A. Don't let these questions intimidate you. If you just organize your information, you'll be good to go. Okay. So now we're going to finish with some nuclear. Here we have a graph. Love graphs. They're great. And here it's telling us about the number of neutrons and the number of protons. We're moving between two different points. So if we're starting here, we're going to have 83 for the number of protons, which is going to be on the bottom. And then 128 is the number of neutrons. So our mass number is going to be 128 plus 83, because mass number is equal to protons and neutrons. Okay, so this will end up being 211 for our mass number. But then what element is that and how do we know? So we know that the number of protons defines what element we have. So we just get our periodic table, look for element 83, and as maybe you already knew, that is indeed bismuth. I'm just going to rewrite that a little bit nicer. We'll have bismuth 211 And then we can see what it becomes. You can see now it has 81 protons and 126 neutrons, which would be 207 for the mass number then. From just adding the protons and neutrons together. So we have to figure out what element that is by looking at the number of protons. And element 81 is TL. Okay, and so then, we can think what process must have happened to make this change. And so we know we need our numbers on top here to be equal to our numbers on top here. So we would need to have a 4 on top to make this also add up to 211. And so then on bottom we would need a 2 to make our bottom numbers add up to 83 like on the left. And so a particle that loses 2 protons and 2 neutrons is going to be an alpha particle. And so this process then would correspond to answer choice C. Then our last problem is also a nuclear question. We have thorium. They give us the half-life. So we didn't look at this in this practice exam, but we know that nuclear decays are always first order. And it's a really long half-life. But we're trying to figure out what's the most likely type of decay for TH 234. So I did find its atomic mass on the periodic table because that can be useful sometime. But let's go ahead and figure out what its atomic number is. And this is where you get to have fun, where you play the find it on the periodic table game. Sorry, I'm losing find it on the periodic table. Okay, silly me. There it is. Okay, so TH has an atomic number of 90, and for this particular isotope, a mass number of 234. And so since its atomic number, which is oftentimes denoted as Z, is greater than 83, that means its most likely mode of decay is going to be alpha decay. And so we can see how this might happen if we just wrote it for one alpha decay. You could think about it shooting out an alpha particle. And so the product then would have to have a mass number of 230 and an atomic number of 88, which would then correspond to element A. Really all we had to do here was look, see its atomic number is greater than 83, boom, alpha decay. So that's all I have for this. I hope that you guys are actually working through these problems, not just watching me do them. It really helps when you put pen to paper and pencils to buttons. And I hope that you are feeling confident going into this exam, and you can do it, okay? You can dominate.